The impact of nanotechnology extends from its medical, ethical, mental, legal and environmental applications, to fields such as engineering, biology, chemistry, computing, materials science, and communications. Major benefits of nanotechnology include improved manufacturing methods, water purification systems, energy systems, physical enhancement, nanomedicine, better food production methods, nutrition and large-scale infrastructure auto-fabrication. Nanotechnology's reduced size may allow for automation of tasks which were previously inaccessible due to physical restrictions, which in turn may reduce labor, land, or maintenance requirements placed on humans. Potential risks include environmental, health, and safety issues. Transitional effects such as displacement of traditional industries as the products of nanotechnology become dominant, which are of concern to privacy rights advocates. These may be particularly important if potential negative effects of nanoparticles are overlooked. Whether nanotechnology merits special government regulation is a controversial issue. Regulatory bodies such as the United States Environmental Protection Agency and the Health and Consumer Protection Directorate of the European Commission have started dealing with the potential risks of nanoparticles. The organic food sector has been the first to act with the regulated exclusion of engineered nanoparticles from certified organic produce, firstly in Australia and the UK, and more recently in Canada, as well as for all foods certified to Demeter International Standards. Overview. Potential risks Potential risks of nanotechnology can broadly be grouped into four areas: health issues, the effects of nanomaterials on human biology; environmental issues, the effects of nanomaterials on the environment; societal issues, the effects that the availability of nanotechnological devices will have on politics and human interaction; speculative issues, the specific risks associated with the speculative vision of molecular nanotechnology, such as grey goo. Health and safety impact from nanoparticles. The presence of nanomaterials is not in itself a threat. It is only certain aspects that can make them risky, in particular their mobility and their increased reactivity. Only if certain properties of certain nanoparticles were harmful to living beings or the environment would we be faced with a genuine hazard. In this case it can be called nanopollution. In addressing the health and environmental impact of nanomaterials we need to differentiate between two types of nanostructures: nanocomposites, nanostructured surfaces, and nanocomponents, where nanoscale particles are incorporated into a substance, material or device. And or nanoparticles, where at some stage in production or use individual nanoparticles of a substance are present. These free nanoparticles could be nanoscale species of elements, or simple compounds, but also complex compounds where for instance a nanoparticle of a particular element is coated with another substance. There seems to be consensus that, although one should be aware of materials containing fixed nanoparticles, the immediate concern is with free nanoparticles. Nanoparticles are very different from their everyday counterparts, so their adverse effects cannot be derived from the known toxicity of the macro-sized material. This poses significant issues for addressing the health and environmental impact of free nanoparticles. To complicate things further, in talking about nanoparticles it is important that a powder or liquid containing nanoparticles almost never be monodisperse, but contain instead a range of particle sizes. This complicates the experimental analysis as larger nanoparticles might have different properties from smaller ones. Also, nanoparticles show a tendency to aggregate, and such aggregates often behave differently from individual nanoparticles. The National Institute for Occupational Safety and Health has conducted initial research on how nanoparticles interact with the body on registered trademark S systems and how workers might be exposed to nano-sized particles in the manufacturing or industrial use of nanomaterials. NIOSH currently offers interim guidelines for working with nanomaterials consistent with the best scientific knowledge. At the National Personal Protective Technology Laboratory of NIOSH, studies investigating the filter penetration of nanoparticles on NIOSH-certified and EU-marked respirators, as well as non-certified dust masks have been conducted. These studies found that the most penetrating particle size range was between 30 and 100 nanometers, and leak size was the largest factor in the number of nanoparticles found inside the respirators of the test dummies. In the Consumer Product Safety Commission and Nanotechnology, E. Muller-Felcher suggests that the Consumer Product Safety Commission, which is charged with protecting the public against unreasonable risks of injury or death associated with consumer products, is ill-equipped to oversee the safety of complex, high-tech products made using nanotechnology. Longer-term concerns center on the impact that new technologies will have for society at large, and whether these could possibly lead to either a post-scarcity economy, or alternatively exacerbate the wealth gap between developed and developing nations. The effects of nanotechnology on the society as a whole, on human health and the environment, on trade, on security, on food systems and even on the definition of human, have not been characterized or politicized. Health issues equals. The health impact of nanotechnology are the possible effects that the use of nanotechnological materials and devices will have on human health. As nanotechnology is an emerging field, there is great debate regarding to what extent nanotechnology will benefit or pose risks for human health. Nanotechnology's health impact can be split into two aspects: the potential for nanotechnological innovations to have medical applications to cure disease, and the potential health hazards posed by exposure to nanomaterials. Nanotoxicology is the field which studies potential health risks of nanomaterials. The extremely small size of nanomaterials means that they are much more readily taken up by the human body than larger-sized particles. How these nanoparticles behave inside the organism is one of the significant issues that needs to be resolved. The behavior of nanoparticles is a function of their size, shape and surface reactivity with the surrounding tissue. Apart from what happens if non-degradable or slowly degradable nanoparticles accumulate in organs, another concern is their potential interaction with biological processes inside the body. Because of their large surface, nanoparticles on exposure to tissue and fluids will immediately absorb onto their surface some of the macromolecules they encounter. The large number of variables influencing toxicity means that it is difficult to generalize about health risks associated with exposure to nanomaterials. Each new nanomaterial must be assessed individually and all material properties must be taken into account. Health and environmental issues combine in the workplace of companies engaged in producing or using nanomaterials and in the laboratories engaged in nanoscience and nanotechnology research. It is safe to say that current workplace exposure standards for dusts cannot be applied directly to nanoparticle dusts. Nanomedicine is the medical application of nanotechnology. The approaches to nanomedicine range from the medical use of nanomaterials, to nanoelectronic biosensors, and even possible future applications of molecular nanotechnology. Nanomedicine seeks to deliver a valuable set of research tools and clinically helpful devices in the near future. The National Nanotechnology Initiative expects new commercial applications in the pharmaceutical industry that may include advanced drug delivery systems, new therapies, and in vivo imaging. Neuroelectronic interfaces and other nanoelectronics-based sensors are another active goal of research. Further down the line, the speculative field of molecular nanotechnology believes that cell repair machines could revolutionize medicine and the medical field. Environmental issues equals. Nanopollution is a generic name for all waste generated by nanodevices or during the nanomaterials manufacturing process. Nanowaste is mainly the group of particles that are released into the environment, or the particles that are thrown away when still on their products. The thrown-away nanoparticles are usually still functioning how they are supposed to, they are just not being properly used anymore. Most of the time, they are lost due to contact with different environments. Silver nanoparticles, for example, they are used a lot in clothes to control odor, those particles are lost when washing them. The fact that they're still functioning and are so small is what makes nanowaste a concern. It can float in the air and might easily penetrate animal and plant cells causing unknown effects. Due to its small size, nanoparticles can have different properties than their own material when on a bigger size, and they are also functioning more efficiently because of its greater surface area. Most human-made nanoparticles do not appear in nature, so living organisms may not have appropriate means to deal with nanowaste. To properly assess the health hazards of engineered nanoparticles, the whole life cycle of these particles needs to be evaluated, including their fabrication, storage and distribution, application and potential abuse, and disposal. The impact on humans or the environment may vary at different stages of the life cycle. One already known consequences to metals exposure is shown by silver. If exposed to humans in a certain concentration, it can cause illnesses such as argyria and argyrosis. Silver can also cause some environmental problems. Due to its antimicrobial properties, when encountered in the soil it can kill beneficial bacteria that are important to keep the soil healthy. Environmental assessment is justified as nanoparticles present novel environmental impacts. SCNIS raises concerns about nanopollution, and argues that it is not currently possible to precisely predict or control the ecological impacts of the release of these nanoproducts into the environment. Metals, in particular, have a really strong bonds. Their properties follow up to the nanoscale as well. Metals can stay and damage the environment for a long time, since they hardly degrade or get destroyed. With the increase in use of nanotechnology, it is predicted that the nanowaste of metals will keep increasing, and until a solution is found for that problem, that waste will keep accumulating in the environment. On the other hand, some possible future applications of nanotechnology have the potential to benefit the environment. Nanofiltration, based on the use of membranes with extremely small pores smaller than 10 nanometers, are suitable for a mechanical filtration for the removal of ions or the separation of different fluids. A couple of studies have found a solution to filtrate and extract those nanoparticles from water. The process is still being studied, but simulations have been giving a total of about 90% to 99% removal of nanowaste particles from the water at an upgraded wastewater treatment plant. Once the particles are separated from the water, they go to the landfill with the rest of the solids. Furthermore, magnetic nanoparticles offer an effective and reliable method to remove heavy metal contaminants from wastewater. Using nanoscale particles increases the efficiency to absorb the contaminants and is comparatively inexpensive compared to traditional precipitation and filtration methods. One current method to recover nanoparticles is the cloud point extraction. With this technique, gold nanoparticles and some other types of particles that are heat conductors are able to be extracted from aqueous solutions. The process consists of a heating section of the solution that contains the nanoparticles, and then centrifuged in order to separate the layers and then separate the nanoparticles. Furthermore, nanotechnology could potentially have a great impact on clean energy production. Research is underway to use nanomaterials for purposes including more efficient solar cells, practical fuel cells, and environmentally friendly batteries. Regulation issues. Significant debate exists relating to the question of whether nanotechnology or nanotechnology-based products merit special government regulation. This debate is related to the circumstances in which it is necessary and appropriate to assess new substances prior to their release into the market, community and environment. Regulatory bodies such as the United States Environmental Protection Agency and the Food and Drug Administration in the U.S. or the Health and Consumer Protection Directorate of the European Commission have started dealing with the potential risks posed by nanoparticles. So far, neither engineered nanoparticles nor the products and materials that contain them are subject to any special regulation regarding production, handling or labeling. The material safety data sheet that must be issued for some materials often does not differentiate between bulk and nanoscale size of the material in question, and even when it does, these MSDS are advisory only. Limited nanotechnology labeling and regulation may exacerbate potential human and environmental health and safety issues associated with nanotechnology. It has been argued that the development of comprehensive regulation of nanotechnology will be vital to ensure that the potential risks associated with the research and commercial application of nanotechnology do not overshadow its potential benefits. Regulation may also be required to meet community expectations about responsible development of nanotechnology, as well as ensuring that public interests are included in shaping the development of nanotechnology. Societal impact. Beyond the toxicity risks to human health and the environment which are associated with first-generation nanomaterials, nanotechnology has broader societal impact and poses broader social challenges. Social scientists have suggested that nanotechnology's social issues should be understood and assessed not simply as downstream risks or impacts. Rather, the challenges should be factored into upstream research and decision-making in order to ensure technology development that meets social objectives. Many social scientists and organizations in civil societies suggest that technology assessment and governance should also involve public participation. The last few years has seen a gold rush to claim patents at the nanoscale. Over 800 nano-related patents were granted in 2003, and the numbers are increasing year to year. Corporations are already taking out broad-ranging patents on nanoscale discoveries and inventions. For example, two corporations, NEC and IBM, hold the basic patents on carbon nanotubes, one of the current cornerstones of nanotechnology. Carbon nanotubes have a wide range of uses, and look set to become crucial to several industries from electronics and computers, to strengthened materials to drug delivery and diagnostics. Carbon nanotubes are poised to become a major traded commodity with the potential to replace major conventional raw materials. However, as their use expands, anyone seeking to manufacture or sell carbon nanotubes, no matter what the application, must first buy a license from NEC or IBM. 2. 3. Potential benefits and risks for developing countries. Nanotechnologies may provide new solutions for the millions of people in developing countries who lack access to basic services, such as safe water, reliable energy, healthcare, and education. The United Nations has set Millennium Development Goals for meeting these needs. The 2004 UN Task Force on Science, Technology and Innovation noted that some of the advantages of nanotechnology include production using little labor, land, or maintenance, high productivity, low cost, and modest requirements for materials and energy. Potential opportunities of nanotechnologies to help address critical international development priorities include improved water purification systems, energy systems, medicine and pharmaceuticals, food production and nutrition, and information and communications technologies. Nanotechnologies are already incorporated in products that are on the market. Other nanotechnologies are still in the research phase, while others are concepts that are years or decades away from development. Protection of the environment, human health and worker safety in developing countries often suffers from a combination of factors that can include but are not limited to lack of robust environmental, human health, and worker safety regulations. Poorly or unenforced regulation which is linked to a lack of physical and human capacity. Often, these nations require assistance, particularly financial assistance, to develop the scientific and institutional capacity to adequately assess and manage risks, including the necessary infrastructure such as laboratories and technology for detection. However, concerns are frequently raised that the claimed benefits of nanotechnology will not be evenly distributed, and that any benefits associated with nanotechnology will only reach affluent nations. The majority of nanotechnology research and development, and patents for nanomaterials and products, is concentrated in developed countries. In addition, most patents related to nanotechnology are concentrated amongst few multinational corporations, including IBM, Micron Technologies, Advanced Micro Devices and Intel. This has led to fears that it will be unlikely that developing countries will have access to the infrastructure, funding and human resources required to support nanotechnology research and development, and that this is likely to exacerbate such inequalities. Producers in developing countries could also be disadvantaged by the replacement of natural products by developments in nanotechnology. These natural products are important export crops for developing countries, and many farmers' livelihoods depend on them. It has been argued that their substitution with industrial nanoproducts could negatively affect the economies of developing countries, that have traditionally relied on these export crops. Effects on labor as equals. Ray Kurzweil has speculated in the singularity as near that people who work in unskilled labor jobs for a livelihood may become the first human workers to be displaced by the constant use of nanotechnology in the workplace, noting that layoffs often affect the jobs based around the lowest technology level before attacking jobs with the highest technology level possible. It has been noted that every major economic era has stimulated a global revolution both in the kinds of jobs that are available to people and the kind of training they need to achieve these jobs, and there is concern that the world's educational systems have lagged behind in preparing students for the nanotech age. It has also been speculated that nanotechnology may give rise to nanofactories which may have superior capabilities to conventional factories due to their small carbon and physical footprint on the global and regional environment. The miniaturization and transformation of the multi-acre conventional factory into the nanofactory may not interfere with their ability to deliver a high-quality product. The product may be of even greater quality due to the lack of human errors in the production stages. Nanofactory systems may use precise atomic precisioning and contribute to making superior quality products that the bulk chemistry method used in 20th century and early 21st currently cannot produce. These advances might shift the computerized workforce in an even more complex direction, requiring skills in genetics, nanotechnology, and robotics. Impact of molecular nanotechnology. Molecular manufacturing is a potential future subfield of nanotechnology that would make it possible to build complex structures at atomic precision. Molecular manufacturing requires significant advances in nanotechnology, but once achieved could produce highly advanced products at low costs and in large quantities in nanofactories weighing a kilogram or more. When nanofactories gain the ability to produce other nanofactories, production may only be limited by relatively abundant factors such as input materials, energy and software. The products of molecular manufacturing could range from cheaper, mass-produced versions of known high-tech products to novel products with added capabilities in many areas of application. Some applications that have been suggested are advanced smart materials, nanosensors, medical nanorobots and space travel. Additionally, molecular manufacturing could be used to cheaply produce highly advanced, durable weapons, which is an area of special concern regarding the impact of nanotechnology. Being equipped with compact computers and motors, these could be increasingly autonomous and have a large range of capabilities. According to Chris Phoenix and Mike Treader from the Center for Responsible Nanotechnology as well as Anders Sandberg from the Future of Humanity Institute, molecular manufacturing is the application of nanotechnology that poses the most significant global catastrophic risk. Several nanotechnology researchers state that the bulk of risk from nanotechnology comes from the potential to lead to war, arms races and destructive global government. Several reasons have been suggested why the availability of nanotech weaponry may with significant likelihood lead to unstable arms races. A large number of players may be tempted to enter the race since the threshold for doing so is low. The ability to make weapons with molecular manufacturing will be cheap and easy to hide. Therefore, lack of insight into the other party's capabilities can tempt players to arm out of caution or to launch preemptive strikes. Molecular manufacturing may reduce dependency on international trade, a potential peace-promoting factor. Wars of aggression may pose a smaller economic threat to the aggressor since manufacturing is cheap and humans may not be needed on the battlefield. Since self-regulation by all state and non-state actors seems hard to achieve, measures to mitigate war-related risks have mainly been proposed in the area of international cooperation. International infrastructure may be expanded, giving more sovereignty to the international level. This could help coordinate efforts for arms control. International institutions dedicated specifically to nanotechnology or general arms control may also be designed. One may also jointly make differential technological progress on defensive technologies, a policy that players should usually favor. The Center for Responsible Nanotechnology also suggests some technical restrictions. Improved transparency regarding technological capabilities may be another important facilitator for arms control. A grey goo is another catastrophic scenario, which was proposed by Eric Drexler in his 1986 book Engines of Creation, has been analyzed by Freitas and some limits to global ecophagy by biovirus nanoreplicators, with public policy recommendations. 4, and has been a theme in mainstream media and fiction. This scenario involves tiny self-replicating robots that consume the entire biosphere using it as a source of energy and building blocks. nanotech experts including Drexler now discredit the scenario. According to Chris Phoenix's so-called grey goo could only be the product of a deliberate and difficult engineering process, not an accident. With the advent of nanobiotech, a different scenario called green goo has been forwarded. Here, the malignant substance is not nanobots but rather self-replicating biological organisms engineered through nanotechnology. Studies on the impact of nanotechnology. The first major attempt to assess the societal impact of nanotechnology was a workshop held at the National Science Foundation, September 28–29, 2000. A second extensive follow-on workshop was held at NSF December 2–3, 2003. The reports of these meetings were co-edited by Miles C. Rocco and William Sims Bainbridge, Societal Implications of Nanoscience and Nanotechnology, Nanotechnology, Societal Implications, Maximizing Benefits for Humanity, and Nanotechnology, Societal Implications, Individual Perspectives. The Royal Society's Nanotech Report, 5, was inspired by Prince Charles' concerns about nanotechnology, including molecular manufacturing. However, the report spent almost no time on molecular manufacturing. In fact, the word Drexler appears only once in the body of the report, and molecular manufacturing, or molecular nanotechnology not at all. The report covers various risks of nanoscale technologies, such as nanoparticle toxicology. It also provides a useful overview of several nanoscale fields. The report contains an annex on grey goo, which cites a weaker variation of Richard Smalley's contested argument against molecular manufacturing. It concludes that there is no evidence that autonomous, self-replicating nanomachines will be developed in the foreseeable future, and suggests that regulators should be more concerned with issues of nanoparticle toxicology. In 2008, the city of Cambridge, Massachusetts in the United States considered whether to institute nanotechnology regulations similar to that in Berkeley, California, the latter being the only city in the United States to currently regulate nanotechnology. The Cambridge Nanomaterials Advisory Committee's final report of July 2008 recommended against such regulations, recommending instead other steps to facilitate information gathering about potential effects of nanomaterials. In July 2003, the United States Environmental Protection Agency, 6, issued the first research solicitation in the area of nanotechnology impact, exploratory research to anticipate future environmental issues. Part 2, Impacts of Manufactured Nanomaterials on Human Health and the Environment. 7. In September 2004, U.S. EPA partnered with the National Science Foundation and the Centers for Disease Control to issue a second research solicitation, Nanotechnology Research Grants Investigating Environmental and Human Health Effects of Manufactured Nanomaterials, a joint research solicitation, EPA, NSF, NIOSH. In August 2005, a task force consisting of 50-plus international experts from various fields was organized by the Center for Responsible Nanotechnology to study the societal impact of molecular nanotechnology. 8. In October 2005, the National Science Foundation announced that it would fund 2 national centers to research the potential societal impact of nanotechnology. Located at the University of California, Santa Barbara, 9. and Arizona State University, 10. Researchers at these 2 centers are exploring a wide range of issues including nanotechnology's historical context, technology assessment, innovation and globalization issues, and societal perceptions of risk. Determining a set of pathways for the development of molecular nanotechnology is now an objective of a broadly based technology roadmap project, 11, led by Battle and the Foresight Institute. That roadmap should be completed by early 2007. In October 2006, the International Council on Nanotechnology based at Rice University published a survey of nanomaterial handling practices being used by industrial and academic workplaces on 4 continents. The survey revealed that more information is needed to protect against the potential occupational risks associated with handling free nanoparticles. ICON also maintains the Virtual Journal of Nanotechnology Environment, Health and Safety, which is a compilation of citations to peer-reviewed studies on risk issues. In 2007, Springer SBM started the journal Nanoethics, Ethics for Technologies that Converge at the Nanoscale. This journal is a multidisciplinary forum for exploration of issues presented by converging technology applications. While the central focus of the journal is on the philosophically and scientifically rigorous examination of the ethical and societal considerations and the public and policy concerns inherent in nanotechnology research and development. Nanotechnology's summary of the assessment on the safety of nanotechnologies by DGSANCO's Scientific Committee on Emerging and Newly Identified Health Risks, Center for Nanotechnology in Society at Arizona State University is a major NSF-funded research center focused on analyses of the societal impact of nanotechnology. American Elements Information Center on the past, present, and future impacts of nanotechnology. See also, Fail-safes in Nanotechnology, International Center for Technology Assessment. References. Further reading, Fritzelhoff, Patrick Lynn, and Daniel Moore, What is Nanotechnology and Why Does It Matter? From Science to Ethics. 12. Fritzelhoff and Patrick Lynn, Nanotechnology and Society, Current and Emerging Ethical Issues. 13. Fritzelhoff, Patrick Lynn, James Muir, and John Weckert, Nanoethics, The Ethical and Societal Implications of Nanotechnology. 14. 15. Koldis, Byron. Epistemology of Nanotechnology. Sage Encyclopedia of Nanoscience and Society http, www.academia.edu Epistemology of Nanoscience, Approaches to Safe Nanotechnology, an Information Exchange with NIOSH, United States National Institute for Occupational Safety and Health, June 2007, DHHS Publication No. 2007-123, Mater, Michael. Jeffrey Hunt. Nanotechnology, Risk, Ethics and Law. London, Earthscan. Provides a global overview of the state of nanotechnology and society in Europe, the USA, Japan and Canada, and examines the ethics, the environmental and public health risks, and the governance and regulation of this technology. Dacubnal P. Mathanaur, Nanoethics, Big Ethical Issues with Small Technology. 16. External links, U.S. National Nanotechnology Initiative, Societal Dimensions, Nanotechnology Now, USC's Nanoscience and Technology Studies, NELSI Global, ASU's Center on Nanotechnology and Society, UCSB's Center on Nanotechnology and Society, the Nanoethics Group, Nanotechnology, Foresight Nanotech Institute, Center for Responsible Nanotechnology, the Center for Biological and Environmental Nanotechnology, the International Council on Nanotechnology, the Nanoethics Bank, Nanoethics, Ethics for Technologies that Converge at the Nanoscale, National Institute for Occupational Safety and Health Nanotechnology Topic Page, Understanding Nano, European Centre for the Sustainable Impact of Nanotechnology.